Okay, and we have been learning several different proof techniques. Can someone tell me at least the names of the proof techniques that we've discussed so far? Proof by contradiction, yep. What else do we have? Yeah, so thank you, that's all of them. So we've got direct proof, we've got contrapositive, and proof by contradiction. Right, and in each of these, we kind of have a picture or a diagram, right? Not a diagram, but for direct proof, we're trying to show something like P implies Q, and you show.
Mr. Besson.
Oh, yes. Oh, is it not focused?
No, sorry.
Oh, yeah, let me take a look and make sure that things look good.
Thank you.
Okay, is that better?
Much.
Great. So we have P implies Q, and we want to show that P being true implies Q being true is true. Because then the implication is certainly true, right? The implication can only be false when I have a true implies false. So if we don't have that, then this implication is true. The contrapositive just turns that around and says, well, you could work with P implies Q, or you could just as well work with Q implies, or not Q implies not P, right? And then proof by contradiction says, if we want to prove P is true, show that not P implies R and not R. Or in other words, not P forces a contradiction. Okay. Let's see. Any questions on this collection of proof techniques? I think that we've covered all of these somewhat, with the most spectacular being the proof by contradiction being used to show that the square root of 2 is an irrational number. Okay, so to finish off section 7, we're going to go through a couple more kinds of proofs. So the first one is called a vacuous proof. And in a vacuous proof, what we do is we want to prove a statement of the form P implies Q. Okay. Let me write out the truth table of P implies Q again. So if we have P, we have Q, and then we have P implies Q, then the truth table, as you all know very well, is true, true, false, false, true, false, true, false. And then P implies Q is true. This is the only case where it's false, true, true. Okay, so the point of a vacuous proof is to notice the following fact, that if I'm trying to prove a P implies Q statement and P is always false, then what is the truth value of P implies Q? Yeah, it's always true. Exactly. So this area right here of the truth table is what a vacuous proof deals with. So if the premise is false, then the implication is always true. a vacuous proof. So, you know, we were playing kind of some fun games at the beginning of class when we were, you know, discussing kind of English language sorts of things. So I can, of course, write some statement like, if I, Mark, have 3 eyes, then the Clippers won Game 7 from the Nuggets. And and can anyone comment about whether or not this proposition is true or false?
It's true.
Right, this whole thing is true because the premise is false. I can guarantee to y'all that I have 2 eyes and not 3. So this whole proposition is false. So anytime that you set up a P implies Q where the premise is false, the whole thing is true. We can do some more mathy examples, of course. So for instance, let's say Pn is the following proposition. Pn is if n is greater than 1, then n squared is greater than n. So here's the proposition Pn, and then we can say, let's determine the truth value of P0. What is the statement P0?
Zero is greater than 1.
It's if 0 is greater than 1, then
Zero squared is greater than 0.
exactly, 0 squared is greater than 0. And a vacuous proof of P0 being true is that I just examine the premise and notice that it's false. Since 0 greater than 1 is false, P0 must be true. I don't even care what the conclusion of an implication is. It's always true if the premise is always false. So this is kind of this feels like you're doing less work than in the direct proof, so the proof by contradiction or things like that. But this ends up being an important proof strategy to have in your toolbox. You need to be able to handle some cases where where the premise is false, and then a vacuous proof tells you the implication is true. Questions on this?
I just have 2 questions about notation.
Okay, sure.
So one, do we need to write out what P of 0 is, or P of whatever, every time we do a vacuous proof?
No, so here I only wrote out this sort of thing. I did this for the following reason. Eventually we'll get to a proof form called induction, where you're trying to prove like Pn is true for all n. And part of the induction is checking what's called a base case, which is usually P0 or P1. And usually those are very simple to prove, for instance, because they're vacuously true or because they're trivially true. So the Pn or P0 thing is not required here. No.
Okay. And also we still need the box, right?
Yeah.
Okay, thank you.
Box. Yep. Good questions. Any other questions? Here's another nice example that's coming straight from the book. here's a vacuous proof. Prove that if 10 is greater than or equal to n, and n is less than or equal to 15, and n is a perfect square, then n is also a perfect cube. So let's prove this. How do we go about this?
You pick any number between 10 and 15.
So here we are, we're going to do that, yes. So we're trying to show that if the following two conditions are satisfied, namely n is in between these two numbers, could be equal, and n is a perfect square, then something else holds. So the numbers between 10 and 15, can they ever be perfect squares? No, exactly, they can't. So the numbers n such that 10 is less than or equal to n and is less than or equal to 15 cannot be perfect squares. Since 3 squared is equal to 9 is less than n, and 4 squared is equal to 16 is greater than n. Right? So all the perfect squares that you can that's it does feel a little shady, doesn't it? Since all of our perfect squares are either less than n or greater than n, thus the statement is vacuously true. So it's not really the proof strategy that's shady, it's the fact that this is how implications work. That implications are true if the premise is false, right? But we've seen examples for why that has to be the case for our logic to work nicely. So I mean, yeah, but I definitely understand the feeling. Let me try to refocus again. Or maybe it's just my handwriting that's bad now. Yeah, it's just my handwriting. Oh, and then we have the box to finish the proof. Any questions on this? Yeah, so vacuous proofs come up. They're an important kind of special case that you have to sometimes deal with. There's a very similar kind of proof, which goes as follows. It's called trivial proofs. And once again, so you're trying to show P implies Q. And I'll write down once again the truth table. P, Q, P implies Q. True, true, false, false. True, false, true, false. True, false, true, true. So my next question to you is, so the vacuous proofs kind of lived here, where we were able to say, if we're always in the case where P is false, well then P implies Q has to be true. So this is the vacuous proof area. My next question is, what about the times when Q is true? If Q is always true, then what is the outcome of P implies Q? Yeah, in a very similar way, P implies Q has to be true in the trivial area. So here, these two cases are the trivial proof area. If you wanted to keep going with this kind of proof area thing, then the direct proof is everything that excludes this area, right? Because what we showed for a direct proof is that P being true implies Q is true. But if P is false, then everything still goes through. So you can think of our direct proof as excluding this place. Direct proofs exclude this. Or direct proofs show this case doesn't happen. Here. So one way of making sure that P implies Q is true is ruling out this one case. Or in easier ways, a vacuous proof is like, well, if P is always false, then P implies Q is always true. And a trivial proof is like, well, if Q is always true, then P implies Q is always true. So these are kind of much easier ways to demonstrate that an implication is true. Let's do an example. So once again, let's show the following. So P of n is the statement if A is greater than or equal to B, and A and B are in Z greater than 0, or greater than or equal to 0, then A to the n is greater than or equal to B to the n. And so now I could ask you, oh, should the trivial proof area include the last row? No. The trivial proof area, just the strategy of a trivial proof essentially says, look at the conclusion. If the conclusion is always true, then trivially the implication is true. So here, let's prove P of 0. What is the statement P of 0?
Would that be 0 is greater than or equal to Bn?
So the A and B are just kind of given, and the n will be the exponents. So
Oh, okay, so it'll be 1.
Right, exactly. There will be ones, but remember, P of 0 is the whole statement. So P of 0 is the statement if A is greater than or equal to B, with A and B in Z greater than or equal to 0, then A to the 0 is greater than or equal to B to the 0. But what is A to the 0?
1.
Or 1, and what is B to the 0?
1.
1, exactly. So here, this is going to be a trivial proof because I have some premise. If A is greater than or equal to B, and A and B are in the integers, then 1 is greater than or equal to 1. 1 is greater than or equal to 1 is just always true, so I don't care what the premise was. Because if the conclusion is true, then I'm done. The conclusion being true means P implies Q is true. So, since 1 is indeed greater than or equal to 1, the P0 is trivially true. Box. Why was the third row used instead of the fourth row to make the statement that if Q is always true? Well, because the fourth row has Q being false. Shreya, does that answer your question? Catherine, I'll get to your question in just a moment.
Yes, thank you.
Right. So the idea is, once again, you have a P implies Q statement. Usually, you have to do some navigation. You have to show, well, if P is true, then Q is forced to be true. Okay. But if you look at this statement and P is always false, then you're done vacuously. Alternatively, if you look at P implies Q and Q is always true, then you're also done trivially. And here, vacuously and trivially are the names of the proof strategies, because if P is always false, then you're in this zone, and P implies Q is always true. And if Q is always true, then you're in this zone, where Q is always true and P implies Q is always true. In general, you want, like, most proofs that you do won't be vacuous or trivial, but there are some important cases where they are. And Catherine, that's an excellent question. We will develop a proof strategy called induction, which handles these sorts of PN statements very well. At this point, probably we could still prove that this is true for arbitrary n. You'd have to have an expression for essentially the binomial expansion. So if you wanted to prove this without induction, you would need to know that a plus k to the n is equal to something. And here would be a to the n plus n choose 1, a to the n minus 1, b plus. So you need to know something a little more to show that p of n is true for all n. We will get to this in this class, but at this moment right now, we kind of don't have enough structure to prove Pn in a satisfying way. Great questions. Any other ones before we move on? And notice that most of our statements are not of this form, right? We have statements like, if n is odd, then n squared is odd. Here, really what's going on is that here is P and here is Q. And if we're dealing with integers, P is not always false, right? Because there are some even integers. And similarly, P or Q is not always true because there exists n squared such that n squared is odd integers. So in these sorts of statements where you're dealing with this, like P is sometimes true and sometimes false, depending on the integer, and Q is sometimes true and sometimes false, depending on the integer. Here, neither the vacuous nor the trivial proof works. You actually have to do a direct proof strategy, basically. Does this kind of make clear the difference between when we use trivial or vacuous proofs and when we use a direct proof? Excellent feedback. Thank you. That shouldn't have been so sarcastic. Thank you, Kyle. Great. So, a little bit of Clementine. What's next? Equivalence. So oftentimes, another kind of statement that we could be asked to prove are proofs of equivalence. These are things like P implies Q, or sorry, the biconditional, which Can someone remind me how this is said or spoken?
P if and only if Q.
Perfect. This is P if and only if Q. And can someone remind me what this is logically equivalent to in terms of implications?
Isn't it P implies Q and Q implies P?
Exactly. P implies Q and Q implies P. So very naturally, what does this suggest to us if we want to prove that P if and only if Q is true? Well, you got to prove both directions, right? So for a proof by equivalence, you essentially do two proofs. You do one proof that's P implies Q, and you do another proof that's Q implies P. So you're absolutely correct that what P if and only if Q means in the logical sense is that P and Q are true at exactly the same times and false at exactly the same times, right? But if you want, since, how do I want to say this? Since we know that P if and only if Q is logically equivalent to P implies Q and Q implies P being true, if I want to show that this thing is true, it's enough to show that this thing is true. This thing is true if this is true and if this is true, because they're joined by an and. And lastly, how can I show that P implies Q is a true statement? It's sufficient to show that if P is true, then Q is true. So does that kind of chain of points kind of make sense? So I think it'll be very nice with an example. And we'll do this exact example. Show n is odd. Should we do odd or even? Let's do even. N is even if and only if n squared is even. So can someone kind of break down for me the two different things that we have to prove?
So we have to prove that n is even, right?
So all of the things that we have to prove should involve both of these things. So one thing that we would prove is that if n is even, then what?
Then n squared is even.
Right, so this whole statement is a P if and only if Q. And what I'm breaking it down into is if n is even, then n squared is even. And yes, if n squared is even, then n is even. So here's the P implies Q piece, and here's the Q implies P piece. And if I show both of these are true by either direct proof or contrapositive, then I've shown that it is the case that P if and only if Q. Are we comfortable with how I'm kind of approaching this problem, or does anyone have any questions?
So will a proof of equivalence always involve different proof strategies also?
Not necessarily. In this case, it'll turn out that it's nicer to do one directly and to do the other by contrapositive, but it doesn't need to be the case. But it's true that it often is the case that you do use different proof strategies in the two directions. And it's often true that one direction is more challenging than the other, perhaps in some way. So let's do this. So let's do proof of first statement. Well, I'll just say proof. We first prove the first statement. We first prove that n being even implies n squared being even. Okay, so what do we do next?
The direct proof.
Yep, direct proof. And how do we start off our direct proofs? Right, we're going to use the definition of even, and we always do this let. So let, I mean, we don't always do it, but for me, it works nicely. So let n be an even integer. By definition, n can be written as 2k for some k in Z. Then what?
Square the definition.
Exactly. Then n squared is equal to 2k squared, which is equal to 4k squared, which is equal to 2 times 2k squared. Thus, n squared is even. So this completes one direction of proof. Now, to show Q implies P, we show the other direction. So now we show the other direction. So now we're trying to prove if n squared is even, then n is even. And what should we do here? What proof strategy should we use to demonstrate this? We could use contradiction. We could also use contraposition, but yeah, we could use contradiction. So we use proof by contradiction. So what is the contradiction of Q implies P?
Not P implies R and not R.
Yeah, so the proof strategy for contradiction is that we'll negate what we're trying to prove, and then we'll derive a contradiction from that. That's correct. But what we first need to do is negate the thing that we're trying to prove. And the negation of Q implies P is Q and not P. So we assume, for the sake of contradiction, that n squared is even and that n is odd. So in symbols, let me maybe write some scratch work. So what I'm trying to show is Q implies P is true. So what I'm going to actually show is that not Q implies P implies a contradiction, R and not R. But the first thing that I do is I write down what the negation of Q implies P is, and to negate Q implies P, it's Q and not P. Is this step clear? Is there any question about how this is how I begin this proof by contradiction? No questions here? Okay. So what can we do with the fact that n is odd? Right. By definition of odd, n is equal to 2k plus 1 for k in z. Then n squared is equal to 2k plus 1 squared, which is equal to 4k squared plus 4k plus 1, which is equal to 2 times 2k squared plus 2k plus 1. Thus, n squared is odd. But n squared is also even. This is a contradiction. Thus, n squared even implies n is even. Box. So a couple comments that I want to make. First of all, very important that when we write out proofs, we use full sentences. Even if we have math symbols involved, they should fit into full sentences. Another comment that I want to make is that it's fine in this case that we use proof by contradiction, but it is kind of a mathematical habit that if you can prove something directly, then you should. And in particular, proofs by contraposition are usually preferred in a certain sense to proofs by contradiction if they exist, right? Like there's nothing wrong with proofs by contradiction, but it's kind of the mathematical style to prove things directly if you can. And contraposition is essentially a direct proof, just, you know, with the order switched around with a logical equivalence. And notice that in this case, we could have used a proof by contraposition instead of a proof by contradiction. I'm not going to make any fuss about that. I just want to let you know of kind of the general habit or style of mathematical writing. Okay. Any questions on this?
Would you put a box whenever you did the proving the first statement?
I would not, because I view this as one proof of one thing. So I'm just proving that n is even if and only if n squared is even. But inside that proof are two kind of sub-proofs. So I'd only put a box at the end here.
So at the end of it all, we wouldn't have to state that n is even if and only if, like to say that we proved that.
That's polite. That's thoughtful. I appreciate that. And so by all means, write down at the end that you have indeed shown what you wanted to show. But this is okay too, as long as you're kind of clearly stating the two parts of the proof and then you prove each of them. This is also okay. Great questions, y'all. Any further questions? Okay, let's do the last stuff in chapter 1.7 or section 1.7. So sometimes we could be asked to prove several statements are equivalent. So an example, which is a pretty reasonable or simple example, is something like the following. A, which is N is, so show the following are equivalent. TFAE is an abbreviation for the following are equivalent. So N is even, N plus 1 is odd. C is 3N plus 1 is odd. And D is 3N is even. So there's an interesting little game that can be played when you're trying to show that a bunch of statements are all equivalent. Essentially, the way that I think about it is I think of a graph. So here, I'm going to have statement A, statement B, statement C, and statement D. One way to show that all of these are equivalent is, for instance, to show A implies B and B implies A. These two arrows show that A and B are equivalent. And then I could show B implies C and C implies B. So now A is equivalent to B and B is equivalent to C, so moreover A is equivalent to C. And then I could also show that C is equivalent to, or C implies D and D implies C, therefore C is equivalent to D. So how many little mini proofs would I have to do here? 6, exactly. I'd have to do 6, which is kind of a lot. But there are other collections of implications that we could use to show that all these are equivalent. Here is another way. I could show A implies B, and I could show B implies C, and I could show C implies D, and I could show D implies A. Right? Because here, if I wanted to get any equivalence out of this, for instance, say I wanted to show from here that B is equivalent to C. Well, I know that B implies C, and moreover, I know C implies D, D implies B, and A implies B. But really what that means is C implies B. Did what I just say make sense? Essentially, this is one of those logical rules where C implies D and D implies A and A implies B. You can conclude from this that C implies B. So essentially, to show that a bunch of statements are equivalent, you need to be able to start at any statement and go to any other statement. Here's one way to do it, where you make enough bridges so that you can always travel from any one statement to any other statement. But here's another way to do it in this kind of cycle. Here's yet another way where we could pick a collection of implications to prove that would prove that all the following are equivalent. If we have A, B, C, and D, we could also prove that A is just straight up equivalent to B. And then we could prove a cycle like A implies D, D implies C, and then C implies A. Here's another collection of implications that if you prove all of these arrows, then you can start at any proposition and end up at any other proposition. Right? If I start at D and I want to get to A, well, A implies D and D implies A. If I want to go between C and B, well, B implies A, which implies D, which implies C, and also C implies A, which implies B. So in other words, when you have a bunch of statements that you're trying to show are equivalent, you need to find some nice graph that looks like this, and then prove all the arrows, which allow you to kind of move from any given statement to any other statement. Does this make sense? So I don't have time to prove it today. And since all these statements are really simple, let's just kind of sketch out which things would be very easy to prove. So which of these things kind of immediately implies something else? Well, n being even immediately implies n plus 1 is odd. That's a very quick thing. Because n is even means n is equal to 2k, and then n plus 1 is 2k plus 1, so n plus 1 is odd. So this one's super easy to do. If n is even, then 3n is even. Yeah, that's fine, because if n is even, n is equal to 2k, and then 3n is 2 times 3k. So this one's super easy. And then you kind of want to fill in the rest of the arrows until you can get this graph structure that I've described. That I'm actually going to just end here today. 2 more minutes is not enough to show much. So have a nice day, and I will I will release your test grades in like 10 minutes. And yeah, please email me about them and chat with me. I'm happy to discuss. Have a nice day, everyone.
Thank you too.
Thanks.
Yep,
Thank
see you all on
you.
Friday.